Welcome to PDC 2008. My name is Sharif Faraj, and I work in the client performance team focusing on energy efficiency.
And my name is Michael Millerud. I'm a program manager on the same team as Sharif, and I own the Windows Performance Toolkit.
So today we're going to go through a hands-on analysis with the Windows Performance Toolkit. The agenda, we're going to start off with the motivation. Why should folks care about performance and energy efficiency? We'll talk about some application best practices, and then we'll actually provide an overview of the Windows Performance Toolkit, followed by two case studies, one focusing primarily on performance, and then the second one focusing on energy efficiency. And then we'll summarize where the presentation, and then we'll finalize, and then we'll give you some resources and follow-up actions. So motivation. Why should you care about performance and energy efficiency? We know that performance directly impacts productivity, usability, and support for larger scenarios. And all of these things sum up to, at the end, customer satisfaction. We know that there's an industry-wide focus on energy efficiency with Energy Star requirements, green computing, and overall just strong focus across the industry to get more energy efficient PCs. The environmental impact of power consumption is very significant. Small wins really translate to large global savings. And what I mean by that is if you save 100 milliwatts on today's PC across the broad range of PCs in the industry, that has a significant impact overall to the environment. There are tools available today within Windows to help identify issues related to performance and energy efficiency. The Windows Performance Toolkit is a great example of that. We've also got inbox diagnostics in Windows 7 to help analyze and identify problems with applications that may be preventing lower power modes. So oftentimes we get asked, what makes a great application? What are the characteristics of a good application? The first thing we look at when we talk about performance is we look at resource efficiency across all scenarios. We look at idle scenarios, we look at active scenarios, and we look at the traditional platform resources, CPU, GPU, network, and look to see how are applications utilizing those resources. But a resource that often gets overlooked is energy. And one thing that when we talk about optimizations in the traditional platform resources, those typically translate to energy efficiency wins as well. So not only should you be looking at platform efficiencies with resources, but also evaluate energy and potentially look at scaling back when you're on DC power to extend mobile battery life. But it's also about AC energy efficiency as well. We also think about responsiveness. How responsive is your application under adverse conditions? A scenario is if your application relies on network connectivity, what happens to your application and the user experience when there is no network connected? Does your application respond correctly? We know that a lack of responsiveness directly impacts customer satisfaction, and that's a key area there. The other characteristic that we look at when we talk about a good application is good citizenship. We know that one application can dramatically impact performance and energy efficiency on the platform. In the follow-on slide, we'll talk about how we view the problem space and what are all the components that really are required to get a great user experience from both a performance and energy efficiency perspective. We want applications to adapt to system environments. What I mean by that is if the application or if the system is on DC power, does your application scale back that experience? Does your application respond to various power transitions gracefully? We also think that applications should look to defer or coalesce non-critical work on the system. So if your application if the system is in a low power state, it's not necessary to wake that system up from that low power state to do non-critical work on the system. And the other aspect of this is just a strong industry focus on energy efficiency. As I mentioned, one application can have a significant impact on the overall energy efficiency of the platform. And it's really requires a concerted effort across the industry to get energy efficiency and performance right on the platform. So as we look at the problem space and how we break down the problem, what are all the pieces that really are required to make an optimized Windows platform? We start with the core hardware, and we know some of the challenges here is that there are higher performant parts and lower performant parts, and there are trade-offs to be made there in terms of what your end users are needing from a performance perspective. We also see on mobile devices the increasing number of devices that are being introduced into the mobile platform. And so some of the things that we're doing in this effort, in this area, are active industry engagements with IHV partners, both looking at today's platforms, but also looking at future platforms and how we can efficiently power manage those devices, as well as introduce performance trade-offs and energy efficiency trade-offs to make the right decisions for the end customer. As we go up the stack and look at the operating system, one of the key challenges here is that each OS release that we introduce additional features into the platform. And that is something that our customers are asking of us. And so we have to be intelligent in how we introduce those features. Are those features energy efficient? Are those features performant? And do they meet our customers' needs? So we look at each of these features and really try to focus on making those features as energy efficient as possible, but also being able to get the system into low power states as often as possible. As we continue up the stack, and this is why we're here today to talk to you, is applications can have a significant impact. The extensions that we talk about, the drivers, the services that are installed, and the applications themselves. One single bad extension can remove all of the optimizations that you've done at the core hardware or at the OS layer. And so it really does require a concerted effort across the entire ecosystem to get this done right. Some of the challenges we have in this area, and one of the things that we will urge you to do in the follow-on slides, is the lack of instrumentation that we have in some of these extensions makes it difficult to diagnose the problem. But we encourage you to instrument your applications or your extensions to be able to use tools like the Windows Performance Toolkit to help analyze problems on the system. As I mentioned, some of the efforts we've done here is we've released XPER for the Windows Performance Toolkit. We've provided a battery life solutions guide to help folks understand some of the things that they should be looking for within the core hardware, within the operating system, as well as best practices within the extensions layer as well. So with that, I'm going to hand it over to Michael to talk about the Windows Performance Toolkit.
Thank you, Sharif. So hello and welcome to this session. What I'm going to talk about is a very cool and very powerful piece of technology, what we call Windows Performance Toolkit, what is also unofficially was called XPER for many years. This tool has been in existence for over 10 years, actually, within Microsoft, and we have finally released it to the public. This is built and used by the entire Windows organization. We're using this to produce Windows builds daily. We're using this to sign off on quality and performance metrics within the Windows product. It has a wide support range. We support this on Windows Vista 2008 and the upcoming Windows 7 and 2008 R2 releases. We support all three architectures, x86, x64, and IA64. And this is publicly available for download today, and I'll show you later how to actually get to it. The kit contains a tool suite called Performance Analyzer, which has a number of different tools that would let you investigate various system activities on the machine running Windows, such as disk, registry, CPU, etc. And you should expect additional tools to come in around Windows 7 beta timeframe. This is a strategic ongoing investment, which is very important to stress, because this is not something we just released for people to use. This is something we continuously invest in and closely work with the Windows product teams to improve and enhance. So here's a big picture of how XPER actually operates, or the Performance Analyzer tool suite. It is based on ECW, so all of the instrumentation that XPER is capturing and then visualizing is actually produced by the event tracing infrastructure in Windows. And there is a number of different providers that can be registered to provide those events. Windows kernel has been heavily instrumental over the past several years to provide very detailed and rich instrumentation, as well as multiple other layers such as Shell, Internet Explorer, and Media Center. XPER is then used to control the tracing, and what that means is that you tell Windows, enable tracing for specific providers and specific events. And you should be very careful about enabling just what you need, because otherwise you will spam the system with too much data. And that's captured into an ETL file. We then do post-processing to inject additional information so that that information could be then decoded on other machines and used by analysts. There's a second tool called XPER View, and that's a GUI environment that lets you open an ETL file and analyze the various usages of resources, as well as show you the tabulated data, which we call a summary table, that lets you really drill into the individual events that are happening on the system, as well as do statistical analysis on them. And there is also support for command line based processing through actions using Xperf. That is very useful for automating performance analysis, and we use this internally in such frameworks as performance gates, which run on multiple builds every single day and try and catch regressions in performance. So with that, let me actually switch to a performance case study. And before I show you the tool itself, let me show you how to get to the toolkit. So it's actually as simple as searching for Windows Performance Toolkit. The first link you'll see will be the MSDN documentation for the toolkit, and the second one is a landing page on the WHDC, the Windows Hardware Developer Central site, that has a short summary of what the tool is about, links to the documentation and several white papers, as well as downloads for all three architectures. In this case, I've already installed the toolkit on my machine to save some time, so I'm not going to install it. But definitely download and install it on your machine. And here's an ETL file that we have created to showcase some of the performance issues. But before we do that, I'd like to just show you how the tool works. So by default, it installs into Program Files, Microsoft Windows Performance Toolkit. And you can see here that there are several exes. Xboot Manager, Xboot Manager Slip, those two are responsible for on-off transition capture, which is standby, shutdown, resume, etc. Xperf exe, this is the main component that you're going to be using all the time to open most of the traces and capture most of the traces. This is used both for trace capture and command line processing. And Xperf View, this is a GUI tool that lets you analyze the traces. You actually don't have to use Xperf View. If you just do Xperf and the name of a file, it will open Xperf View for you. There is an extensive help subsystem within Xperf that you should definitely benefit from, in addition to MSDN documentation. And the things I would start with as you explore the tool is do Xperf-help start. That will show you the various options of how to capture traces. And Xperf-help symbols, that will show you how to load symbols once you have the traces. With that, let's actually open up a trace. And show you how the tool is used in real life. So I'm typing Xperf Performance ETL, and that is going to open Xperf View and load up the trace. And you'll notice the bigger the trace, the longer it takes to open it up. This trace in particular is 96 megabytes, so it's a pretty substantial size trace, and we still open all the millions of events very fast and show you an aggregated view of all the usages in the system for various resources. So what you see here is a number of different graphs, what we call usage graphs. There is a CPU sampling by CPU graph that actually goes, and for every single CPU on the system, and in this case there was only one, it samples at 1 millisecond rate what was happening on the system, and then shows you just how much percentage-wise the CPU was used over the course of the 2 minutes that this was captured at. Another example of an interesting graph is CPU frequency and CPU idle state, and Sharif will mention this more in the next case study, and this shows you the power-related aspects of the CPU. Then there's the disk I/O and disk utilization graphs, and this is a histogram, this is a usage graph, and they both show you how the disk is being used by the system within the period of the trace. This is aggregated on a per 10-second bucket size, and it shows you all of the reads and writes and flushes that were happening on that disk. And disk utilization is just like CPU sampling, is actually showing you, modeling the disk and showing you just how much the disk was used. Was it used at 100%, at 50% of its capacity? There is a process lifetime graph that actually lets you understand where you are in the trace, because usually what happens is you start some scenario, you start an application, and you want to understand the startup cost of it, and you can actually see exactly when the process was started or ended. And various additional graphs, DPC, ISR, various faults, etc. As you read the documentation, as you investigate the tool, you'll find quite a lot of those useful. With that, let's try and actually drill into this particular trace. We got this trace from a guy that was complaining that he was trying to mark 875 messages as read in Outlook, and it took him about 2 minutes to do that. And he was not really understanding why that is the case, because he had a pretty fast system, a lot of memory. And he was asking, why does it take 2 minutes to mark just 800 messages on my modern machine? So looking at the CPU, we're actually seeing that CPU doesn't take that much time, right? On average, it's maybe about 25%. Obviously, for those 2 minutes, the user was waiting on Outlook to deliver, in this case, some result. And it wasn't bottlenecked on the CPU. If you continue drilling down, you will see that there was a lot of disk activity. At any point in time, there was up to 1,500 or more disk IOs a second, not a second, at 10 seconds interval, which is about 150 IOs a second. And we know that on average, a current disk can handle maybe 80 IOs a second, and that's a good thing to handle. So the disk was obviously overloaded with disk IO requests. And if you look at the utilization, fair enough, this is pegged at pretty much 100%. And the only reason you don't see a completely steady 100% line is because our instrumentation is not granular enough to actually show you that. We're not sampling fast enough. But this is really about 100% disk utilization. But before we drill into disk, let's first actually look at the CPU. And for that, I would want to load symbols to actually show you what's going on the system. So let me find, great. Microsoft. So I will be using a local SIM cache. You would actually have to download the symbols from the public symbol server externally. But we have a local SIM cache that we can use. And right now my system is actually set to use a public symbol server. So I will switch that. SIM cache path. SIM cache. And then I will set the symbol path to SRV SIM cache symbols. Right. And let me close and reopen the trace. You do have in the current version of the toolkit to open the trace with the symbol set up beforehand in the environment variable. In the upcoming version, we'll actually add GUI support for this. Export performance ETL. Can I configure it? TW SIM cache. No, that doesn't seem to work. There we go. So I was trying to download the SIM caches from a network, and it seems like my machine is actually not connected to the server. But I do have some local symbols, so let's hope that will be enough. So let's again select the CPU usage graph. Do load symbols, and then open a summary table. Summary table is the secondary level of analysis. So what we use graphs for is to find out where the issue is. It's a first level triage. You see where the resource bottlenecks are. You try to understand what it is that you need to concentrate on while analyzing the trace. Then as you find out the resource bottleneck, you look at the data in a tabulated form within a summary table. This is actually an extremely powerful spreadsheet. It may look like Excel, but it's actually much more than that. It lets you aggregate millions of data points and collapse them and group them so that you can easily search what you need to find in the trace. So in this case, we are grouping by process, then module, then function. And if you'll notice this gold bar, it is separating what is being grouped by from the actual data points that are being aggregated. So if you drill in on this idle process, you will see that there are a lot of different modules and different functions that are running within the context of the idle process. All of those modules are drivers for obvious reasons, but they all combine together to 67% of CPU usage. So within that 2-minute period in a trace, for 67%, CPU was not doing much. It was idling, which is great for Sharif's performance and energy efficiency concerns, but it's probably not great when the user is waiting for Outlook to do something useful. And you see that Outlook, in fact, was only doing 5% of CPU activity. Very limited. So we will go to what we call a flyout. If you notice this triangle on the left, and we will select stacks. And I can actually get rid of module and function because stacks are far more powerful. And as I drill into the stack group, which is an aggregation of all the stacks. Again, you have to think of this as the tool is aggregating all the multiple data points into something common. In this case, RTL user thread start, which is the first function that starts calling into Outlook code in this case, is spending 5.13%. This is the individual samples, and we have 6,145 instances of those samples that were always hitting in that function. And as you drill in, I unfortunately don't have symbols for Outlook to show, since those are internal. But as you drill in, and if you were to load the Outlook symbols, you would see that Outlook in this case is actually correctly marking messages as read. So we are looking at the right code. For some reason, it's only taking 2% in this case of CPU usage. And the question is why. So as we saw before, let me go back to the graphs. We saw that disk usage was very heavy. So let's try and drill into to the disk usage. So I'll select the region where it's at back to 100%, and I'll go to summary table. This is the summary table for disk usage. And it's right now grouped by path name first and process second. Before we do that, let's actually go to process first and path name second. And we are sorting by service time. So this is actually sorted by service time. And you'll see that search indexer is taking 40 seconds. This is in microseconds, so you see 39,654,548 microseconds. So that's about 40 seconds. So about 40 seconds was spent waiting on disk from search indexer, and then about 30 was spent from the system, which is a system process that handles most of the system activity. Then there is svchost.exe. This is a general container process that lets you host various services code. And there is trusted installer. About 8 seconds were spent there waiting. And Outlook, right? So we have 5 different processes heavily using disk. And you can see that search indexer spent about 1,900 reads and 900 writes. And then system spent about 1,500 reads and also 900 writes. And one thing I would like to point out here is that Outlook, which is supposed to be doing a lot of activity, has done 5,500 approximately writes, which makes sense, but only 8 reads. That doesn't necessarily make sense. Why would Outlook not be reading anything? And Vista has a feature called superfetch, where OS is smart enough to pre-cache and preload into memory data that it thinks the application is going to be using. And in this case, this is working perfectly because system knows that Outlook is about to access its PDC or OST file locally, and it's pre-caching it in memory beforehand. So by the time Outlook actually asks for data, it's already in memory. And that's why the 1,500 reads are mostly due to that. So if we now sort by path name first, or group by path name first and then process, you can actually see which files are being accessed the most. And you'll see that the first file that's accessed the most is Windows EDB under the Microsoft Search Data Application folder. And this is the JET database that Search Indexer is using to index all of the files on the system that is actually tracking actively. Then there is Outlook.ost, not surprisingly. So 35 seconds are being spent waiting for disk IOs related to Outlook OST. And this tells us this is on an Exchange server. This is not a local PST file. Then there is a data store EDB. That's a JET database for trusted installer. This is where all of the applications installed on your system and all of the Windows Update information is stored. And pagefile.sys is also being accessed quite a lot. With that, let's actually go back to the graphs and look at another type of a graph. All the graphs you've seen so far are the various usage graphs, histogram graphs in the main view of XPerf. There is also notion of detail graphs for some of the graphs, such as the disk utilization. So let's select the detail graph and see what's going on in the system. This is a visual representation in time of how the disk was actually operating. Every single seek is represented by a gray line connecting dots, and dots can be reads, writes, or flashes. The legend up in the top right corner actually shows you the various processes that are accessing the disk. And each process has its own color. You could actually, if you have preferences with colors, you can actually go double click and choose whichever color you want for any given process. But let's see which of those processes are actually taking the most usage of the disk. So I'll hover over the various points, and I'll see that all of those dots here in red are Outlook OST accessed by Outlook.exe, which is process 6908. And then all of the blue dots are also accessing Outlook OST, but on behalf of the system. So this really shows us that system is touching Outlook OST file. It's pre-caching, pre-reading for Outlook. And then there's another big distribution of color here, and that's search indexer. And one more is trusted installer. So with that, let's try and deselect everything and select just Outlook, search indexer, trusted installer, system. And I believe there was also one SVC host that was doing a lot of activity, right? So what you see is that there are 5 processes out of 20 or 30 something processes running on the system touching the disk that are continuously fighting over the disk, and it almost looks like an earthquake. The seeking head is going up and down on the platter. The offset actually represents where it is on the platter throughout time. So most of the time is not spent reading or writing, it is spent seeking. And studies show that seeking can actually cut throughput by up to 90%. 90% is order of magnitude. That means instead of taking 5 seconds, which is what you measured in the lab, and what probably the Outlook developer signed off on, in this case, the scenario is taking 50 seconds, 100 seconds, or even more. And that is definitely very bad. This particular example is actually a case where multiple applications are fighting for disk. And we have done a number of improvements in Vista SP1 to try and be more graceful about how we use disk from the various components involved here. So you should not see that happening on your systems. But imagine your component, your application that is actually accessing disk and trying to access some significant data store. Have you tested it with other applications that are using disk? Have you tried it with other applications heavily using disk? How does it look like? So try and think of this when you test your application. And with that, let me switch back to the slides. And just quickly reiterate on the case study that we've seen. System resources are a finite and shared resource. You cannot assume that you're the only person or the only component on the system that's using them. You have to play nicely and actually use them only when you absolutely have to. High usage of any single resource is going to invariably cause performance issues. There's just no way around it. Unless you're dedicated box and the only thing that you're doing is running your code, you will have to deal with performance issues when you're using single shared resources. And high CPU in particular, when you use a lot of CPU usage, you will be preventing other threads from running. And that could mean responsiveness issues. It could mean throughput issues. Invariably, as Sharif has mentioned, this means customer satisfaction issues. High disk usage, like we've seen in this case, can prevent other applications from accessing the disk in a timely fashion. And that can slow down your scenario by up to an order of magnitude, by up to 10 times. So we advise you to focus on your core scenarios and look at the resource utilization in those core scenarios. Capture traces, see where is the bottlenecks are and how you're using those resources. And ensure that your application doesn't actually try and steal the resources from the rest of the citizens on that system. And with that, we will switch to a second demo of energy efficiency. And Sharif will present that.
Thanks, Michael. So I'm going to walk through a case study. So I'm going to walk through a case study on energy efficiency. And before I jump in, I want to provide a little background on what we look at when we look at energy efficiency on the platform. This graph here shows an idle system, and it's an idle system running about at 15 watts when the system is idle. What we show here on the x-axis is what happens to CPU as CPU utilization increases. What happens to the power consumption on the system? And a 10% increase in CPU increases the power consumption on that platform by 1.25 watts. That's pretty significant, but what does that translate to in terms of battery life? That's about a 8.3% reduction in battery life, a fairly significant impact to the end customer's experience and degrading battery life significantly. Now, clearly, applications when the system is idle really shouldn't get to significantly high CPU utilization because that is the opportunity for the system to really enter low power states. But why do we look at idle so much? And the reason why we look at idle and really focus on that is idle is the baseline from which all other workloads are going to be derived from. What I mean by that is a system that's consuming 17 watts, any other workload is going to increase over that. So really focusing on getting your idle activity down on the system is important. It also is the biggest opportunity for power savings on the platform. When the system is truly idle, and we expect that to be pretty frequently, we really have a great opportunity to get that system into a significantly low power state. So really what I'm saying is idle really dominates all other workloads. Even if you think about it from an active scenario and a user using their system in an office productivity scenario or doing some other email through web browsing or whatnot, those scenarios have large periods of idle time within them. And so getting the idle floor to as low as possible is critical for improving energy efficiency on the platform. So with that, I'm going to walk through a demo, and this case study that I'm going to show you is a derived case study. So we've written an application that exhibits problems that we've seen on various systems that are actually running from end users. This scenario, though, it kind of exaggerates a little bit the impact of these scenarios to really bring home the point. So I'm going to switch to XPerf again, the Windows Performance Toolkit, to show you the trace that we've captured. So again, this was a trace that was captured using XPerf, and what we see here is the various graphs that Michael's kind of walked through, but the system was idle. And what we see immediately is the CPU utilization, again, somewhat exaggerated, but we see the CPU utilization pretty high, and it seems to be pretty periodic in time. So we can come in here and look at the CPU usage. I'm going to turn on, oh, sorry, I have this graph down here. I'm going to come down here and look at what the CPU usage is on this platform over just a period of time within the trace. And as I see here, the first line shows that I'm idle about 80% of the time. But I have a PDC hands-on lab application, which is consuming 10% of the CPU during that period of time in the trace. That's fairly significant. Again, one of our guidelines or one of the recommendations that we make is when the system is idle, even with applications opened, but the user is not interacting with the system, we really would like to see that we're not consuming more than 2% of the CPU on a typical dual-core system today. That seems like a fairly good guideline, and the reasons for that are what I'll show here shortly of the impact this has on processor power consumption and overall system power consumption. So I see here that I have an application that's consuming about 10% of the CPU. And as I look down here, I can come here and look at this graph, which is very interesting, which gives me CPU usage by process. And I can click over here and shut off a bunch of applications and only turn on the ones that are of interest to me. So I can see what's happening to the PDC hands-on lab application, and I'm driving up CPU usage periodically every 10 seconds on the system. So what does this mean to power, and how does this relate? So the first thing I want to show here is the CPU frequency graph. On today's modern processors, the OS works in conjunction with the hardware to control the P states of the platform. And what that means is it's actually, based on usage, is controlling which frequency and which voltage the system is running at. And the higher P states translate to higher power consumption on the system. So as we can see here, most of the time within this trace, we're actually at the lowest P state on the platform, which is what we would expect, that on a truly idle system, we should be 95% or greater in the lowest P state. However, whenever I see this activity occur within the PDC hands-on lab application, I see that I increase my P states due to that activity. So again, translates directly to power consumption, both from a processor perspective and obviously from an overall system perspective. The other thing I can look at is the C states on the system, and these C states are what's considered idle states of the platform. So on today's modern platforms, various C states will allow you to shut off parts of the processor and save additional power. And again, what I see here is on the system, as my pretty much lockstep with my application. I can come here and clone this section and see that when I have this activity, not only am I increasing the P state, but I'm actually turning on portions of the processor that I had previously turned off. Again, a significant impact to overall energy efficiency. So that's one thing that I've looked at here and looking at processor utilization and processor activity, but I think there's more to this trace, and I want to go and identify additional problems. The first thing I see here is disk utilization. So I see that my disk utilization is fairly spiky and periodic in time, and that really prevents the disk from spinning down. That's another great opportunity for power savings on the platform. By allowing the disk to spin down, we can save as much as 1 to 2 watts on the platform to conserve power. And there are power policies within Windows that determine when to turn off the disk based on how much activity it's seen over the past period of time. So as I come in here and look and see that I have my disk utilization is high, I really want to understand what's causing that. And I also see a bunch of registry activity, and so I really want to drill into that first. So I'm going to select a region in this and come in here and look at the summary table for that. So I see a bunch of processes that are accessing or doing things to the registry, and so I want to drill into that a little bit more, and I can expand each one of these processes and look to see what's happening. Now, obviously, there's service host.exe, which is doing things within the registry, but in general, what we're seeing here is that the operations that they're doing are simply querying or opening the registry that don't necessarily cause disk activity, because oftentimes that registry information is cached. So what we do see is flushes and set values within the PDC hands-on lab application. Again, pretty significant amount of time is being spent just doing flushes and set values, whereas a lot of these other applications are simply querying or opening the registry. And again, with that being cached, doesn't necessarily translate to immediate disk activity. So I can come in here and look at that. I'm going to close this up and look at the disk activity on the system and see exactly what's happening. And again, as I highlight here, we spent a significant amount of time within the PDC hands-on application writing to certain log files on the disk due to this. And again, that's immediate power savings loss, because if the disk was spun down, we would be spinning up the disk. So understanding when it's absolutely critical to write to registry or flush the registry is something that application developers should really look at. If that disk is spun down and you're spinning it up, your power is being lost on the system, and again, that translates to increase in power consumption even on AC, and as I've mentioned earlier, with industry focus around Energy Star and driving down PC consumption regardless of state, this should really be looked at carefully. So overall, I've shown you a sample example of an application that, again, somewhat exaggerated in some cases, and periodic in nature. Applications should really look at all activity on the system and really, from an energy efficiency perspective, focus on idle first. That is the key thing to focus on. Ensure that your application is as energy efficient as possible during the idle scenario. That obviously does not mean to ignore the performance optimizations that are done during active scenarios, as Michael's alluded to, because those are also good for energy efficiency. But the first step to look at is really looking at idle on the system. So with that, I'm going to summarize the case study. As I've mentioned, CPU power has a wide dynamic range. When the system is truly idle, the innovations that are being done by the IHV vendors are really trending towards 0 watts when the system is idle. And on mobile systems, they're as high as 35 watts when active. Again, this example showed periodic activity and the impact it had on power consumption, but any activity on the system can have a significant impact. It may prevent the CPU from entering low power states to begin with. It will cause the CPU to exit low power states, and that's absolutely a critical thing to understand, is that if we're in a low power state and we have to exit, sometimes that conserves or costs more in terms of power consumption of entering and exiting those low power states. Disk and registry flushes will prevent the disk from spinning down. So really focus on the impact that your application has on the resources that it's using. And as I mentioned, first and foremost, focus on resource utilization at idle. With your application open and no user activity, what's the impact or the footprint that your application has with regards to resource utilization and energy impact? In addition, if you focus on idle optimizations will benefit most scenarios on the platform, as I have alluded to earlier. So with that, I'm going to hand it back to Michael to go and summarize and provide some additional resources for you.
So let's try and summarize what we've seen so far. We've seen the Performance Toolkit, and this is a new set of tools that lets you both understand the system activity and optimize your application to work well on Windows systems. And we have concentrated on two primary areas, performance and energy efficiency. The two are quite related, and in many cases, optimizing for performance only also wins you the energy efficiency. But in other cases, you do have to drill in on energy efficiency, specifically in idle scenarios, as Sharif has mentioned. Both of those are key differentiators. What does it mean? It means that those are competitive advantages you can have against other products on the market. Anything that is more responsive and more performant and is going to last long on battery is going to be preferred by customers. And to get good performance and good energy efficiency, you really have to concentrate on three tangible aspects, and that is responsiveness, effective resource utilization, not using more than you need, and as far as the energy, getting idle and staying idle. Overall, this means being a good citizen. It means not using more than you have to, not littering the system, and being always responsive to your end user. And we would like to have several calls to action for you. One is go and download the Windows Performance Toolkit. We have shown you the website, and this will be also available in resources as a link. We also invite you to go and look at the SDK available with your PDC kit. It has the up-to-date latest version of the Windows Performance Toolkit, which is version 4.3, and what's on the website is 4.1. So you should get about 6 months of additional features and improvements in the toolkit if you get the version from the PDC SDK. Start by capturing a trace for your core scenarios, and evaluate where are your resource bottlenecks, where it is that you're using too much CPU, too much disk. Look at both the active and the idle state. Look at both how you are executing on the scenarios in your application, as well as what are you doing when the user is not touching the system at all. Make sure you don't use disk, you don't use CPU unless you absolutely have to. And like we said, ensure that your application that doesn't prevent from going to low states by just getting idle and staying idle. Also invest in ETW instrumentation. We have added a whole bunch of ETW events throughout the operating system, both at the core level of kernel as well as the upper layers of Shell, Internet Explorer, and Media Center. But you will gain additional benefit by adding ETW instrumentation to your component. Because what you can then do is you can overlay the graph with individual events on top of, say, CPU usage or disk usage or registry usage, and see where it is exactly that your scenario is running. That gives you a frame of reference. It lets you drill in much easier on the areas in the trace that you need to understand. And we have a forum available for you publicly where you can ask questions and share your war stories of what works and what doesn't. This will also be available in the resources slide next. So let me briefly go through the resources. The first link is the Toolkit landing page that I've already shown you previously in this talk. The second page is the MSDN documentation. We have a wealth of documentation for the tools available on MSDN, as well as a downloadable CHUM included with the toolkit as well. The third link is a link to the portal of energy efficiency. This covers the various things you need to do to be energy efficient in your component. And specifically, we would like you to go and read through the Battery Life Solutions guide, because that concentrates on how it is that you can actually optimize your code to better work on Windows in terms of using battery. The following link is the Windows Performance Analysis Forum. This is a forum where you can ask questions, you can share your stories, give us feedback of what works, what doesn't, and what you would like to see happen in the tools moving forward. And then there is the link to the documentation about ETW, the event tracing for Windows. You should refer to that resource for adding additional instrumentation to your component. And the last resource, not really a link, is a book on Windows internals called Windows Internals. It is right now in the 4th edition, and the 5th edition is about to be printed very soon, authored by Marcus Sinovich and David Salomon. This book is absolutely must-have reference if you are going to be serious about performance analysis. You can probably get by with 101 basic OS knowledge to try and understand where the resource bottlenecks are. But once you really drill into the code and try to understand what's going on, this book will be invaluable to understand what DPCs mean, what ISRs mean, what disk I/O means and how it actually works, how flashes impact your system, how memory usage works on the OS, etc. With that, we are done with our presentation.